Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to begin looking at Chapter 8, which is on evaporation. We're not going to be doing it very thoroughly. We're going to do sort of a quick overview of this. So first, let's start by talking about just exactly what evaporation is. I think that everyone knows about how things evaporate, but it's the process of removing the vapor from a boiling solution, boiling simply meaning that it is got two phases in equilibrium, so that you are left with a more concentrated solution. So the goal of evaporation is about removing a portion of the liquid to the vapor phase. In order to keep this condition at the boiling point, you are going to require heat input, and there are various kinds of ways we can do this. So open kettles or solar evaporators are some common low-tech ways to do this, but circulating evaporators and falling film evaporators are also in common use. The analysis for this, because we are looking at this mass movement from the liquid to the vapor, and energy input is going to require a combination of mass and energy balances, incorporating phase change, which is going to require solution thermodynamics. So the math can get a little bit complex fairly quickly. Some of the things that are going to affect the rate of evaporation are going to be things like just what is the concentration in the liquid, because that drives our phase equilibrium. But solubility, how much of the material can be dissolved into the liquid. And then there's going to be temperature sensitivity issues, or whether as this material is boiling, does it foam or froth? What pressure or temperature are you operating at? Is there any scale deposition that's happening? That will change your properties of your heat transfer. And what materials are these things used to, for the evaporation equipment? Metals are going to transfer heat better than plastics, for instance. There are lots of different kinds of evaporation equipment. So open kettles or pans, but there are many others. Horizontal tubes, vertical tubes, they can be natural circulation or forced circulation. Long tubes or just short tubes, falling film, forced circulation, agitated film, or open pan solar evaporators. We'll look at some of these. So here is an open kettle evaporator. It's really very simple. It's just an open pan in which liquid is boiled. You're going to supply heat through the walls, either a jacket or you can maybe put a fire underneath that kettle. You might stir it or agitate it. They're really simple to operate, but they're energy inefficient. Another type is the horizontal tube natural circulation evaporator. These are going to use a tube bundle, kind of like you would have in a heat exchanger. Steam is going to enter the tube and condensate will leave the tube, so that's going to be how you can quantify your heat transfer. The tubes are covered by the process fluid that's going to be concentrated and will cause that process fluid to boil. This will work pretty well as long as you don't get fouling outside of the tubes, and these are a continuous operation. There are also vertical type natural circulation evaporators. These use short vertical tubes. The liquid is inside the tubes. You're going to get this movement, this convection due to the change in density by your boiling, which will cause some natural convection. You're going to have steam condensing on the outside of these tubes, so that's what makes it different than the ones we just looked at. Sometimes the tubes are set up actually as a basket so that they can move through the steam on the outside. These work pretty well as long as you have a relatively inviscid fluid, but with heavier viscosities, think of trying to get syrup to move through the inside of these tubes. This would be fairly difficult. Long tube vertical type evaporators typically mean that the tubes are going to be 3 to 10 meters long, and the liquid is again going to be inside the tubes, and the vapor bubbles inside the tube will be what actually causes the motion. Steam will flow outside the tube, and typically you're not going to recirculate this liquid, so it has to do all of its evaporation while it is still inside those tubes. A falling film evaporator is kind of like, just think of a single tube, a fairly wide diameter tube with fluid falling along the edges, and so kind of like a waterfall almost. So these typically get used when you have really heat sensitive materials. So like orange juice concentration is typically done in a falling film evaporator. You do get high heat transfer coefficients with this, and there's a very small holdup time, so the material will not stay in the device for very long, just simply because you're allowing it to fall due to gravity. Forced circulation evaporators have the fluid pumped around so that it keeps recirculating until it is condensed enough. This is going to be a useful design when you do have those more viscous fluids, so think syrups, something like that. An agitated film evaporator just simply adds turbulence to the system. So it's like the falling film evaporator, but now then you're going to stir that falling film so that it's more turbulent. So again, it's going to be good for those heat sensitive materials like we had before, but I can also deal with viscous fluids in these cases. So like latex, gelatin, fruit juices, these are all good cases for an agitated film evaporator. They tend to be more expensive and have a small capacity, but they are very easily controlled. Open pan solar evaporators are both old technology and new technology. Solar is in these days. Typically what you use these for is like you're going to place salt water in a shallow open pan and then just wait for the sun to evaporate all the water and leave behind salt crystals so that you will have salt for your food. Now, there are different ways that we can operate these, and we're going to focus on the steady state operation of these evaporators. And a single effect evaporator basically is going to be that you're going to bring your process fluid into your evaporation device, and it spends a certain amount of time there. Heat will be added, and the process fluid will leave, and in the meantime, we evaporated, say, our water out of this. So this was my dilute solution, and this is my concentrated solution. Very simple. But we also can have multiple effect evaporators, and these can happen in lots of different ways. So you're going to have multiple evaporators, first of all, but now then it depends on what I'm doing with my fluids. So if I bring in a feed, and I'm heating it with steam, the steam leaves as condensate, as we see here. The material will be more concentrated and taken off the bottom. The vapor from this can be used to heat the next effect. So now that I'm not having to add fresh steam, I'm just going to now condense this steam. The fluid that left the bottom of the first evaporator goes to my second evaporator, and so forth, and we can repeat this with as many evaporator stages as we have. These also can be a backward feed, so this one's a little bit more complicated to first look at, but I'm going to bring in my process fluid. So notice my feed is over here on this side. So I'm going to bring this in to the first evaporator, and I'm going to have steam heat this, and I will have some liquid that comes off the top. That's going to go be reclaimed in a heat exchanger, and then I will have my more condensed or my more concentrated, material. That's going to be taken out of this and into another stage. And again, out of this and into another stage until finally I have it as my final product. In the meantime, I also have my steam. My steam comes in, leaves as condensate. In each one, I'm going to have steam that is created. So this steam is going backwards compared to the direction of flow of the process fluids, which are going from 3 to 2 to 1. Okay? Now the analysis still is going to require the same mass and energy balances, but I'm going to have different given input conditions. So we're going to, in our next class, we're going to start looking at these mass and energy balances. Thank you for your time.